Today's lesson, we're going to review some properties of surjective, injective, and bijective maps. To do so, first let's review some definitions involving functions. Let's let capital X and capital Y be sets. We'll use the notation f going from x to y to denote a function. This means given a lowercase x and uppercase x, we want to map that to some lowercase y and uppercase y. Simply put, f of lowercase x equals lowercase y. We'll denote the set capital X as the domain of our function f, and we'll denote the set capital Y as the codomain of f. Given a function f, we can consider the set of elements lowercase y and uppercase y that seem to come from some lowercase x and uppercase x. That means we want to consider the set of lowercase y that equal f of lowercase x for some lowercase x. This collection of elements y is called the range of f, and sometimes we'll call this the image of f. It is the subset of the codomain y. Similarly, given a subset U of our codomain y, we can consider those elements lowercase x that map to an element of U. In other words, we want to consider those lowercase x and uppercase x such that f of lowercase x is an element of U. We will call such a set the preimage of f. Sometimes we'll call this the inverse image of f. It is the subset of the domain x. As a caveat, notice that when we write this symbol f to the minus 1, we are not assuming for the moment that this is a function. This is simply a matter of notation, realizing that we want to consider what happens for our set U as it appears inside of the domain x. Here's a picture of everything that we've covered so far. On the right, this red oval you'll see corresponds to our domain x. On the right, you can see a blue oval that corresponds to the codomain y. The yellow oval sitting inside of y will be our image or our range. You can see that the arrows going from left to right correspond to our function. They take a lowercase x inside of the red oval and map that to an f of x inside of the yellow oval. Let's let f be a function. We'll try to review some definitions here. We say that f is well-defined if f of x1 equals f of x2 whenever x1 equals x2. Sometimes we'll just simply call this a morphism. Now this may seem a little bit strange, but let's try to review an example here of one that is not well-defined. Consider the following function, mapping from the rational numbers q to the integers z. Given a rational number, let's denote this as p over q, let's simply map that to the numerator p. We claim that this map is not well-defined. Here's the reason why. Consider the rational number 1 divided by 1, which we know is equal to the rational number 2 divided by 2. Now, according to the naive definition we have of our f of x1 is simply the numerator of x1, namely 1. However, f of x2 is the numerator of our rational number x2, which is 2. Of course, you might say that this is a little bit silly because we really just wanted to pick the numerator if p over q have no factors in common. Well, that's the idea of being well-defined. We would have to be very careful to add in that one statement, i.e., we can write down this map as long as p over q have no factors in common. Of course, we didn't do that here, so that's why we would say that this function is not well-defined. We say that a function is an injection if f of x1 does not equal f of x2 whenever x1 does not equal x2. Sometimes we'll use the fancy phrase and call this a monomorphism. Here's an example of one that is not injective. Consider the function going from the real numbers to the real numbers that sends the number x to its square, x squared. This map is not injective because while x1 equals -1 and x2 equals +1 are different, their images, f of x1 equals f of x2 equals 1. They are the same. Hence, this function, while being well-defined, is not an injective map. We say that a function is a surjection if, for any element lowercase y and capital Y, there exists a lowercase x and capital X such that y equals f of x. Sometimes we'll call this an epimorphism. Here's an example of one that is not. Consider the function, as before, mapping from the real numbers to the real numbers. It says sends a number x to its square. This map is not surjective because there is no real number x such that f of x equals -1. Putting all of this together, we'll say that a function is a bijection if it is well-defined, injective, and surjective. That is, that it does satisfy the two properties listed above. It is a monomorphism and an epimorphism. Sometimes we'll just simply call this a bimorphism. As a warning, we're going to reserve the words homomorphism and isomorphism for later on in our lectures when we introduce maps that preserve a given binary operation. That is, maps that will somehow be related to groups. Now let me draw some pictures here to hopefully explain some of the ideas that we've listed so far. Here's a picture of a function going from our domain x to our codomain y that takes numbers 1, 2, and 3 and maps them to letters A, B, C, and D. You can see here that each of the numbers on the left in the domain maps to a unique letter on the right in the codomain. That means that we actually have an injective map. However, the letter C in the codomain does not come from any of the numbers in the domain. So we said that this map is not surjective. To repeat, here we have a well-defined function that is injective, but it is not surjective. So this is not a bijective function. On the other hand, let's consider a function that maps the numbers 1, 2, 3, and 4 to the letters B, C, and D. You can see that the 4 numbers map to only 3 letters. In fact, the numbers 3 and 4 map to the same letter, the letter C. That means that this map is not injective. However, each of the 3 letters in the codomain comes from at least one number in the domain. So this map is indeed surjective. Again, we have a well-defined map that is not injective, but it is surjective. And so according to the definitions from before, this again is not a bijective map. Finally, let's consider this map here that maps each of the 4 numbers, 1, 2, 3, and 4, to each of the 4 letters A, B, C, and D. You can see here that the 4 numbers map to a unique letter, therefore the map is injective, and each of the 4 letters comes from a unique number. So this map is surjective. Again, we have a well-defined map that is both injective and surjective. So according to our definitions, this is a bijective map. Now there's a different way in which we can put all of these definitions together. This is a matter of saying that the following words and phrases are all one and the same. Say that F is a well-defined map. The following 5 statements are equivalent. We've seen before that we can define a map as being injective using the same word monomorphism. And what this means is, if x1 is different from x2 in the domain, then we want f of x1 to be different from f of x2 in the codomain. What's a little bit surprising is that this idea of being injective is the same as having a left inverse. That means that we can find a function g mapping from y to x such that g composed with f is the identity map on the domain x. We can write a similar idea once we consider surjective maps. As we said before, being a surjection has the same title as being an epimorphism. That simply means, given an element lowercase y in the codomain, capital Y, there exists at least one x in the domain, capital X, such that y equals f of x. Similar to before, we can actually find that such a function has a right inverse. That means that there should exist a function h going from y to x, such that f composed h. Notice how the order here is different from the last theorem. That is the identity map on the codomain y. I'd like to explain how this is related to linear algebra for those that are familiar with the subject. Say that we have a linear transformation going from a vector space of dimension n, Fn, to a vector space of dimension m, Fm. And here it doesn't matter whether f consists of the real numbers or the complex numbers. As we learn in linear algebra, such a linear transformation is equivalent to matrix multiplication. Here we may start with an n-dimensional vector x and end with a m-dimensional vector y, where y is simply a times x for some m by n matrix A. We'd like to ask the question, when do we know that such a linear transformation is injective? Well, using the rank nullity theorem, we can actually prove that such a linear transformation is injective if and only if the kernel is the trivial subspace. This happens if and only if the rank of our matrix is n. N in this case would be the number of columns. One can prove that this is equivalent to saying that there is a linear transformation S such that S composed with T is the identity transformation, which is equivalent to saying that there should be a matrix B such that B times A is the identity. Notice here that we would say B is a left inverse for the matrix A. Now, we are not claiming at all that M equals N. M and N may be completely different numbers. This is completely a statement about having a left inverse. It's a complete statement about the kernel of our transformation. But now, what if we talked about surjective maps? Similarly, the rank nullity theorem would say that our linear transformation is surjective if and only if the image is a non-proper subspace. That is, that the image equals our m-dimensional vector space Fm. This is equivalent to saying that our matrix has rank m. M in this case would be the number of rows. This is equivalent to saying that there's a linear transformation S such that T composed with S, notice how the order is different from the last theorem, is the identity transformation. And this is equivalent to saying there should be a matrix B such that A times B, again you'll notice the order is changed, is the identity matrix. In this case, B would be a right inverse for a matrix A. We'll end by explaining how all of this is related to the concept of a permutation. Again, let's say that our F is a well-defined map. Now we can piece together the concepts that we've listed so far, that is, being an injective map and being a bijective map. We've seen before that being bijective means that we have the two properties, that is, that our map is both injective and bijective. That's equivalent to using the word bimorphism, which, if you recall, means that we have a map that is both a monomorphism and an epimorphism. We also know that we have to have inverses, that is, a left inverse and a right inverse. So this is equivalent to saying that our function f has a two-sided inverse, namely a function g mapping from y to x, such that g composed with f is the identity map on the domain x, and f composed with g is the identity map on the codomain y. We'll use this now to make a definition. We'll say that g is the inverse of f. G, remember here, is the two-sided inverse, and we'll denote this now by f to the minus 1. Putting all of this together, given now a set A, we'll say that a map sigma going from A to A is a bimorphism or a bijection if it's a permutation. We can put the collection of permutations together into a set, which we'll denote by S sub A. Again, S sub A is the collection of all permutations, that is, all bijections mapping from A to A. We have three statements. First, the identity map that sends lowercase a to lowercase a, that is, it just simply is the identity map on our set A. This is a permutation, that is, it is a bijection. Next, if sigma and tau are two permutations, then the composition is also a permutation. Remember, to be a permutation, we need to know that there is a two-sided inverse. Well, explicitly, we can list what it is. The inverse of the composition sigma circle tau is simply tau inverse circle sigma inverse. Notice how the order here of the tau and sigma are slightly rearranged. Finally, If we consider circle here to be composition, then we actually have a group. That is the pair SA, again SA is the collection of permutations from A to A, and circle here is composition, that pair will be a group. In the next lesson, we'll discuss more about this group because this here will be the symmetric group for our set A. Thanks for watching.